In this session, we will talk about the Byzantine fault and the Byzantine fault tolerance concept in distributed systems. One of the things that the Bitcoin blockchain is attributed with is its capability to solve the Byzantine fault by introducing a very innovative concept called proof of work. But before we try to understand the proof of work as a concept, we need to understand what is the problem that we're trying to address. When it comes to the Byzantine fault in distributed systems, there are multiple ways in which the problem is represented and discussed. First one is interactive consistency. So when it comes to distributed systems, their ability to perform a certain task depends a lot on how they interact with each other. And the fault that we're talking about is manifest when there is some sort of an inconsistency in that interaction, which is why this consistency is attributed to how a certain system is able to solve the Byzantine fault. The other name for it is source congruence, which is the ability for a certain source of messaging in a distributed system to be congruent and consistent when it comes to data exchange or information exchange. Error avalanche is a situation when there is a massive error replication or distribution in a distributed system due to the Byzantine fault as an existing condition in the system. Byzantine fault is the lack of an agreement that different components of the system exhibit, which is why it's also called the Byzantine agreement problem. And there is a historical concept or connotation which refers to a group of armies attacking a city, which is very similar to a system not being consistent and being incongruent when it comes to performing in synchronization. So that's where the term Byzantine is originating from, and we'll take a look at that as we get to the later slides. Categorizing or understanding what is meant by a certain fault in a system, let's try to understand what these categories basically represent. So a fault is anything in a system that causes it to behave unexpectedly, and this unexpected behavior can be of three kinds. It could be an intermittent failure, which means it occurs after a couple of maybe transactions in the system or interactions in the system. It can also occur from time to time, as in after a random duration has passed, and that's the intermittent nature of this fault. Transient fault is the one that happens just once and goes away. Nevertheless, its occurrence is recorded. And then finally, the permanent type is the one where the fault continues to stay and manifest itself till it's addressed. For the manifestations of the Byzantine fault, we need to understand what we mean by the situation that results in the Byzantine fault. What happens is, when a distributed system is working and trying to achieve certain results, a certain part of or a certain component of the system can present a fault which is symptomatically different to different observers. A Byzantine failure is the loss of a system service due to Byzantine fault in a system that requires some sort of a consensus. Now the term consensus has a deeper meaning, but when it comes to distributed systems, it makes sense to understand consensus as agreement, where all the components or a minimum number of components of the system have to vote or have to show their consent to a certain update to the system, which means that the system arrives at a certain consensus. And this fault is something that tries to keep the system from arriving at that consensus. The objective of a certain tolerance to this fault in the system is to be able to defend itself from such a faulty component which keeps it from arriving at a consensus. Now this ability can be enhanced if that component is fail stop or fail silent. A fail silent fault is the one where the component or unit just stops functioning but doesn't produce any output, which means that it is very easy to detect that the system that a certain component in the system is no longer working, and the system can flag that component as non-functional. The other type of failure, which is not fail silent, is the Byzantine type. A Byzantine type failure is the one where the unit continues to run but produces incorrect results, and the problem is intensified because it appears to be faulty to certain set of systems who are observing it, but appears to be correct to the others. So this is a very acute problem because it is very hard to detect, primarily because the faulty unit is not really faulty according to some parts of the system, and that is where consensus is a casualty, because achieving consensus in such a system is always prone to be susceptible to an error that you cannot detect. And when it comes to trying to remedy this problem, one of the simple and obvious ways is replication. A replication or failure masking is a situation where parts of the system are replicated so that a faulty situation can be rectified by replicas. So if there is a system that has a primary set of data and that's backed up, whenever that primary data and its components turn faulty, it is possible to fall back to the backup. In practice, when the primary is fixed, its role can be taken over by backups till that fix is in place, and that is where a system becomes crash fault tolerant, primarily because it is able to tolerate a failure that results from a crash by quickly identifying that certain part of the system is no longer functioning and a replica has to be resorted to. There is another term when it comes to distributed systems faults, which is said to be K fault tolerant. K being the number which is the minimum number of components that even if are at fault, the system can survive, which means if the components fail silently and they are all below K, then the system is going to be fault tolerant to that fail silent situation. So this K number is kind of important to understand the resiliency that the system offers. Now we come to the formal definition of the Byzantine failure. Given a system of n components, t of which are not functioning in the Byzantine way, then assuming that the communication between different components is only point to point and not client server, then the situation is said to be a Byzantine fault. Whenever that component, let's call it A, it tries to broadcast a value x, the other components discuss whether that x is consistent as per the entire network or the entire distributed systems consensus, and settle on the value x if only a minimum number of systems agree with it. If A is honest, then all the honest components will agree that the value is x. But in any case, when all the honest systems do not agree to whatever A is broadcasting, the honest set of systems values are going to override what A is broadcasting. So this is the problem, and in part the solution of that problem. Now let's link it back to the earlier discussion around the historical context. And there is a story behind this context when we say that the fault is Byzantine in nature. This history is that there was a time when a certain city was attacked by a group of armies. The city had its own defenses, and the group of armies, they had camped around the city. One of the challenges that the group of armies had was that they had to attack together or simultaneously for them to be able to succeed. And this problem introduced a need to communicate between the commanders or lieutenants of the armies, so that they can synchronize their time of attack or they can synchronize on their time of retreat. In such a situation, if one of the army group's lieutenant became dishonest, what he could do was communicate attack command to one group and communicate retreat command to the other group, which means that one group just retreated and the other group attacks, and what that would result in is an unsynchronized attack and the failure of the attack. So this problem, purely because of the way in which a certain lieutenant can incorrectly and correctly send out messages, results in the Byzantine problem or the Byzantine generals problem. One of the things that was identified was, if in a system of or a group of interconnected components, n number of components could be susceptible to fail in the Byzantine way, then we need at least 3n plus 1 system for the rest of the network to be able to recover from that failure. So we need 2n plus 1 number of components to honestly operate for the Byzantine fault to be tolerated. There are many algorithms that solve the Byzantine problem, and one of the popular ones is the practical Byzantine fault tolerance or PBFT algorithm. So one of the things that PBFT proposes is that a message from a particular node is faulty if the message is not received within a certain time limit. Now with this precondition, it is kind of possible to detect and isolate the failures which are of the Byzantine type. So one thing to understand is we are not saying that the system has to be correct. We are just saying that the message when it's received is not received within a certain time limit. What this means is that if we can ensure that every system is given a time limit for them to respond to the network, then it is possible to at least identify and isolate the systems that are not honest or not working correctly, and then take some remedial measures. So the set of nodes in a PBFT enabled distributed system are, as a way to address this, sequentially ordered, with one node being the primary leader node, which is taking lead in all of the operations, and the other is referred to as secondary. So at any point in time, a PBFT enabled distributed system will have one node, and rest of the nodes are going to be secondary. And obviously the goal is to help reach a consensus regarding the state of the system by using the majority. With the most common PBFT algorithm, there are 4 phases. The client sends a request to the primary node. So we have a client to the system that's operating to use the services of the system. It sends a request to the primary, and primary broadcasts that request to all the secondary nodes. Then the primaries and secondaries together perform the requested task and then send back the reply to the client. And this reply is served successfully only when the client receives m+1 replies from different nodes in the network with the same result, where m is the maximum number of faulty nodes. So the client needs m+1 replies to be assured that the system is giving the right response. There are a couple of limitations of this. One is that only when the number of nodes is small, then can this be a really practical solution, because of the amount of communication that has to happen for the system to operate correctly. Then it is prone to Sybil attacks, where if a certain party which is dishonest is able to control a majority of the nodes in the system, then they can give responses that are inherently incorrect, and the system by and large responds incorrectly. Then finally, scaling is a big problem. As the number of nodes increase, the messaging overhead also increases, and if the number of nodes increase by the amount k and the messages that are needed is n, then the increase is to the order of O(n) to the power k. And since this increase is there, the time taken for messages to be responded to, or the time taken for clients to be responded to, is increased. So with that high level overview, we can take a look at one of the projects that implements PBFT in a certain defined way which is easy to understand. It uses the Redis server, and we can do a walkthrough of the code and see how it runs. So let's go over to the demonstration and see how it operates. Thank you. Hello friends. After that high level discussion on the practicalities of Byzantine fault and how systems can tolerate the Byzantine fault, we will take a look at an implementation project that supports the protocols specified by the PBFT algorithm, or the algorithm that gives a practically Byzantine fault tolerant system. So this project that we will take a look at, it's a project that's open source and available on GitHub. It is built in Java, and one of the things that we have to be aware of during this training is that we will take a look at projects from the open source ecosystem to exemplify some of the concepts that we will be talking about in the conceptual phases of this discourse. So this project is called PBFT Java. You can reach it very simply by googling PBFT Java on your favorite browser. The first link that it shows is that specific Java project on GitHub, and what you'll find is that it's a project that is approximately 2 years old, not a lot of updates since then. For the most part, the project is an implementation of the PBFT protocol with some approximations and divergences for simplicity. So it has two basic specifications that it implements. One is the client specification, and the other is the replica or the node specification. Once we check out this project, we'll have a quick walkthrough of this code, and we will also try to understand what are these specifications and how they interplay. The example directory has most of the code that will run this project, and we will try to run it in Eclipse, which is our preferred Java environment for development. Before we do that, what we have to understand is that we have to be familiar with how the Java environment operates and what are the ways in which we can check out a specific project from open source repositories like GitHub or some of the other locations. It is encouraged that for those of us who are not familiar with some of that, they can look at some simple tutorials and discussions on the internet to understand that in a bit more detail. But just to be able to get up to speed and ramp up, we will discuss some of those basics over the course of some of the demonstrations we'll do as this course progresses. So for checking out this project, you will have to go to the training code repository directory, and for semester 2 module 1, there are a couple of directories that have the source code that has been used for demonstrations. You can go into the Byzantine directory and we'll see it's empty. We open this directory on the console. The system that we are on right now is Linux Ubuntu 20.14, but the same set of instructions with slight variations can work on most of the platforms. So the first thing that we do is we run the git command to clone this repository locally. So we will be using git primarily for cloning projects, and the command to use is git clone followed by the repository name. We will not be checking in any code or managing any repositories, so it's enough to understand that we are using a package called git with a command called clone for most of the demonstrations in the course of this discussion. So what this will do is, if your machine is connected to the internet, it will check out or clone the pbft java repository master branch on your local machine, creating a folder pbft java. Inside this directory you'll see all of the repository artifacts getting created. You'll see each one of them has its own Maven project and the Java files that form a part of the project. So another thing that one has to be familiar with is the Maven build tool, which is going to be used very frequently over the course of various demonstrations that we will go through. One of the primary roles that Maven is going to play is just for us to be able to build the projects that we'll try to demonstrate. We may not need to or prefer to go in details on what Maven does or provides, but for those of us who want to understand the Java build system, it is encouraged to study the Maven project and the options that it offers separately. It is not the scope of this discussion to have a detailed overview of Maven. In these demonstrations, we will be just using Maven for building the projects. So we've checked out the specific project. All we will do is use the Maven's primary artifact pom.xml, which is going to be a part of most of the projects with the same name, to build the project and download all the dependencies that are needed to run the project. The third thing that we will be using is Eclipse. So Eclipse version 2020 or one version earlier are the two versioned tools that we will be using for building and walking through most of the code in various projects. So as you can see, when we launch Eclipse, it's going to ask for an empty workspace directory, which we will have to create for Eclipse to be able to do its bit. So what we've done is, with each project we will be creating a new workspace to be able to separate out the project work. It's by default pointing to this workspace directory inside our module directory. So once launched, Eclipse is going to create its own workspace details or its own configuration inside the workspace directory, and it's going to open this wizard page from where we can import the project. So the option that we have to select is import projects, although there are a bunch of options. Since we are not building a new project, we don't need those. Once we click import project, we have to select Maven on the wizard screen and then select existing Maven project. It's going to ask for the root directory, and the specific root directory that we have to provide it is the one that's right inside the project's root directory, which is pbft java in our case. Just be sure that the directory has a pom.xml, which is what Maven needs to describe its build structure. Once selected, you will see all the projects appear in the import wizard window. Once you click finish, it will import the project as a Maven project and try to build it. This project does not have any errors, so you'll be able to see it built very simply with all of the different projects that it consists of. So as stated, it's got the specification for replica, which is another name for an individual node in a Byzantine network, and then it's got a specification project for the client. So in each one of these specifications projects, you'll see the basic entities like the client, which describes how a client's supposed to operate with some basic functions like send request, checking a timeout, receiving a reply, all of those defined as interfaces. Similarly, in the replica project, you'll see a replica defined with the same almost similar set of interfaces that we'll need for a node to operate. So one of the things that we have to understand is that this interface can be implemented in various ways. The project developer has implemented a specific way in which these could be structured. So when you enter the implementation or IMPL project, you will see that there is a default replica that's already implemented, and this provides high level protocol specific implementation of each of the interfaces that are implemented, that are described or that are declared in the specifications project. So you will see basic functions like check timeout, resend reply, receive request, all of which are a part of the PBFT protocol. So not going into the details of how these operate, what we'll first try to do is see the project working through a basic execution of the project example. So in the example directory, what we'll see is there are various execution start points. Main is the most important one. What it does is it starts up a replica pool, and then it adds various clients to the replica. One thing that this project uses is a database or data store called Redis. It's not necessary to know how it operates on Redis. All we need to know is that all of the test data that it produces, it needs to store it somewhere, and it uses the Redis pool to store that data and operate the PBFT protocol. So although this system already runs Redis, you may want to go to the Redis page and understand how you can install Redis for your specific system. If you are running Ubuntu 20.4 or even 18, you can use the Redis install that that's available by default. The best way to install Redis is run the apt install command and install Redis server. Although this system already has it, we're just going to run it. What it tells me is that Redis server is already installed and it's at its newest version, so it's not going to install it. On new systems, you will see a set of commands that are going to configure Redis once you run this command. So to be able to see whether Redis is running, you can test the status of the Redis service using the system control status Redis command. You should see an output like this that confirms that Redis is healthy and running. Once we are confirmed that Redis is running, all we have to do is run this main class file using the Java application run on Eclipse. So to be able to reach here, what you have to do is right click, look for run as, and click on Java application. What will happen is it will launch this console, and this console will show you the set of operations that are executed as a part of the PBFT protocol for this project. So you will see that there are some send operations, some replica operations, and then an interleaving of send and replica operations, which help the client connect to replicas, and then finally the execution of 6 replicas that have been created, and then finishing of the project run. So once you are able to test this out, you're good to use this project and its implementations in whichever scenario or custom development you want. One thing that you can get is, in case your Redis is not running, which we can test here, then you will get an error which tells you that the connection has been refused from the Redis server. To be able to test this project, you have to have the Redis instance running on your system. So you see, after Redis is started, it's able to execute as expected. So although we did not do a detailed code walkthrough, this is an easy implementation of the practical Byzantine fault tolerant algorithm. You are encouraged to take a look at some of the code comments to be able to understand how the code is operating, and it's a demonstration project that will be able to give you a good idea of how the Byzantine fault tolerant algorithms operate. Thank you.